There are four main things that we want to focus on for this unit. First one, we talked about a little bit, defining science and scientific method. We talked about. We're going to get deeper into experimental design and how to use data and measurements. Okay. So we did define science the other day. Pure science is research that adds to a body of scientific knowledge, and then it really has no practical use. So then technology is how we apply the science. So applied science or technology is the practical application of scientific knowledge. So like research into nuclear physics could lead to applications like nuclear weapons, nuclear power, etc. Medical treatments using radiation therapies. So pure science would be, say, human genetics, okay, decoding the DNA, polymer science, seeing how materials, synthetic materials form chains and go together on a chemical level, atomic theory, figuring out what the atoms are made out of, studying the human ear would be a pure science, like the anatomy and physiology of hearing. An applied science, or the technological use of the science for human genetics, DNA fingerprinting, used in criminal cases, used on Maury Povich when he does the maternity testing. Lycra, Spanx, spandex, that's a polymer. Atomic theory could lead us to nuclear weapons. Unfortunately, they could cause a lot of destruction, but there's a lot of other great applications to nuclear technologies. And that's, like I said, medicine. There's so much nuclear medicine that has helped people over the years. A great positive use for studying the human hearing would be hearing aids. Okay, so science and technology, there's a pure science for science sake, and then the technology is the applied science. And we talked about scientific methods. I used the plural, but your basic scientific method starts with a hypothesis, which is a testable prediction. And theories are explanation as to why phenomena happens. Theories are based on many observations and experimental results. It's repeatable. Scientific law is a prediction of what? It's describes a pattern that's found in nature all the time, consistently. And theories and laws are well accepted by scientists, but they are not set in stone. We're open to new information in science, so they're revised when new information is discovered. What you want to do in a scientific mindset is determine a problem, make a hypothesis, which is more than just an educated guess. It's looking for a relationship. It's looking for a cause and effect. Test your hypothesis, analyze the results, and draw conclusions. Sometimes those conclusions can lead you to retesting or totally new answers. All right, so let's, for example, determine a problem. When the Titanic sank, what happened to the water level on shore? So people would say, if the Titanic sank, then the water level rose, or the water level dropped, or the water level stayed the same. And is this something testable? Sure, you can build a model of it. You can have a tank or a tub, right, filled with water, and put a model of the Titanic in there and see what happens. So that's one way I would suggest testing the hypothesis. Be having like a tank, like a fish tank or an aquarium would be an easy way to test that. And analyze the results. So you would have to have some kind of measurable levels of water. All right, what happened during the test? Those are your data and observations. And drawing conclusions, was your hypothesis correct? Like, let's say you said the water level would rise if the Titanic sank. Did that happen? And then you have to say, well, why or why not did that happen? Uh, was my test valid? Okay, so if I did the Titanic in a fish tank, well, the scale is way off. Obviously, the ocean is this massive amount of water, huge amount of space, and a fish tank is very, very small. So, how accurate was your model? Okay, so you can always draw conclusions and see what you could do in the experiment better. And is further testing necessary? So this kind of leads us to experimental design. A definition of an experiment: it's just an organized procedure for testing a hypothesis. Here's what every good experiment has. The key components are: there is a control. The control is your standard for comparison. The control doesn't get experimented on. And you want to have a single variable. It's too difficult to test more than one variable at a time. So you want to keep all of your factors constants. And you want repeated trials for reliability. The greater the sample size, the better it is. A great model organism would be bacteria because you have many of them and they reproduce quickly. A very poor model organism would be an elephant. Okay, it takes a long time to grow an elephant. Think about that. A good model for a swimming pool might be a fish tank, but for a ocean, the fish tank might not be a good model. There's such a size difference. Okay. Let's look at the types of variables. I'm gonna continue hammering this into you all the time. Independent variable starts with an I. I adjust it. So if you're the experimenter, you adjust the independent variable. This is what you vary, okay? And the dependent variable is going to react to anything that happens to the independent variable. So the dependent variable changes in response to the independent variable. The dependent variable is like what you would measure. So if I were to turn the heat up in the room, that would be the independent variable. And then you could take a thermometer and measure the temperature of the room. That would be dependent. Our hypothesis: let's pretend we are going to store popcorn in the freezer and that will make it pop better. All right. If I put popcorn in the freezer, it will pop better. That's an okay hypothesis. It doesn't get too specific, doesn't say how much or how better it is, by what percent or by how many kernels. But if this was your hypothesis, you would want to have a standard or a control. The control in this case would be the popcorn that's stored at room temperature. You don't do anything to it. And since we have a single variable, that would be our temperature or our storage temperature. That's good. What are our constants? All right, we want to keep the same brand of popcorn. You don't want to have one fresh and one old, right? You don't want to keep one in the freezer for a longer or a shorter time than you would keep one at room temperature. So you want to be as precise as you can by keeping these things constant. You'd probably want to cook them the same way. You wouldn't want to have one on the stove and one in the microwave. So popper would have to be constant. Okay, so we say our independent variable is what temperature the popcorn kernels are stored at. Our dependent variable, something we can measure, is the number of unpopped kernels. So when we're done popping our popcorn, if the cold popcorn had more kernels, we would think that, okay, that probably has an effect on it. But if they turned out with the same amount of kernels left over, the unpopped corn, then we might safe to say that storage temperature really didn't play a role. All right, I'm going to stop right there.